Hello and welcome to the FTS Wildfire Wednesday webinar series. We will be getting started in just a few minutes as we wait for everyone to join. Hey everyone, we're just waiting a few more minutes for people to join. This is the FTS Wildfire Wednesday webinar series. Welcome, we're so glad you're here. Just a few more moments. Okay, well, let's get started. Hello, thank you so much for joining us. Today, we're going to be talking about lightning detection for wildfire events with FTS and our friends at Earth Networks. I'm your moderator, Anna Porteous, and I'm the Director of Marketing at Earth Networks. We welcome your questions and feedback today. If you would like to ask a question, please use the question section of the GoToWebinar control panel. And if you want to follow up after the webinar, please email us at info@earthnetworks.com. Participants are in listen-only mode to minimize noise. This webinar session is being recorded, and you'll receive a recording of the webinar and slide deck in an email after the session. If you can't hear us, please make sure your speaker volume is turned up. You can also listen to the audio by selecting Join by Phone in the audio selection of the control panel. If you're still having trouble, try closing and then rejoining the session. Today's webinar will be presented by Sean Bethel of FTS and Dr. Jeff LaPierre and Steve Principali of Earth Networks. Sean Bethel is the Director of Business Development and Wildfire Mitigation Specialist for Forest Technology Systems. Sean has 35 years of experience in wildfire management and recently joined FTS to take their successes of working with wildfire agencies and predictive services into the utility sector that is contending with wildfire threats and developing their wildfire mitigation plans. Dr. Jeff LaPierre is lightning scientist at Earth Networks and is responsible for performing scientific analyses and case studies using data from the Earth Networks Total Lightning Network. Dr. LaPierre joined Earth Networks in 2017 and has more than 10 years of experience studying lightning physics and chemistry. He is a co-author on several peer-reviewed papers and is a frequent contributor to scientific conferences. He holds a PhD in atmospheric physics from New Mexico Institute of Mining and Technology and a BS in physics from Bishop's University. Steve Principali is program manager and meteorologist at Earth Networks who supports government and enterprise clients such as NOAA, NIST, energy and utilities, value-added resellers, and researchers with their data needs. Steve joined Earth Networks in 2008 as a broadcast meteorologist and is the product manager for Earth Networks Total Lightning Network and its derivative products, including the newly released Historical Lightning Archive. Steve has a BS in meteorology from Penn State University. And now it's my great pleasure to hand it over to Sean Bethel of FTS.
Thanks very much, Anna. I hope you can hear me okay, everyone. Have we got audio there?
You sound great, Sean.
Okay, excellent. Well, welcome everyone, and so pleased to be co-hosting with Earth Networks today for webinar number 3 of 12 that we're offering through the summer until November 2020. It's our Wildfire Wednesday webinar series. First, want to thank you, Anna, for all your great work in preparing us for this webinar today. And there's a lot of pre-work that's involved. And special thanks to Dr. Jeff LaPierre and Steve Principali for joining us. Super interested in the topic today. You know, lightning's very interesting to me and many of the people I'm sure joining us today. So thank you for sharing your knowledge and experience with regards to lightning today, gentlemen. You know, I always try to surround myself with people much smarter than me, and today would be no exception for sure. So similar to our other wildfire webinars, you know, our focus has been more of the power utility, wildfire mitigation planning focus, but we hope that everyone participating today, no matter where you're from or what specific interests you have, you'll have some useful takeaways from this webinar. And, you know, we encourage people to participate in the poll and feel free to ask questions at the end of the session. You know, for me, lightning has impacted me in many unique ways. Firefighting on the ground for quite a few years, and working in the air with you know, air attack resources, and just in general life. But I find it both interesting, intriguing, but also recognize it comes with some associated danger as well, especially related to wildfire risks. So before I get into you know, the sort of little miniature sort of case study with lightning and how it relates to wildfire, just a quick introduction about the Advanced Environmental Monitoring Group. You know, 370 years of combined expertise with 400 industry experts across 7 different companies, including Earth Networks and Forest Technology Systems. And these are, you know, market-leading brands in terms of obviously lightning with Earth Networks, but also precision weather and climate monitoring systems, sensors and software for agricultural sectors, anything hydrological, whether it's flood warning, monitoring, alerting, also air quality is another area of you know, expertise that we offer, and more specific and more to the topic at hand in the wildfire situational awareness areas of interest. So just a quick context about where I come from, and you know, my background and experience in wildfire and how it's relevant to today's webinar and discussions. Where I am sitting right now, where I live, is on that little island on the far left, in the bottom corner of it. The left portion of that geo map there is British Columbia, where I was born and raised. 232 million acres in size, just roughly twice the size of California state. As you can see, the color maps there showing a lot of different geoclimatic zones, a lot of biodiversity. 60% of it's forested, and we have a very significant wildfire regime here. You know, many wildfires every summer. They're starting. I've been hearing helicopters buzzing around our airways around here. There was a wildfire just last night, not far from here either. So it's on. Climate change is also underway. We're seeing an upward trend of wildfire behavior relative to our weather, with an also secondary impact on our vegetation and the fuel that's out there. Definitely an uptick in the amount of fire that's burning, and seeing much longer wildfire seasons, as everyone's well aware of. So what I wanted to do is, you know, some of the utility events I've attended and, you know, sat on panels with, you know, with the likes of, say, Brian D'Agostino and Chris Arends, John Waldemariam from San Diego Gas and Electric, also, you know, Tom Erlinski from SoCal Edison. And, you know, these are trailblazer companies and trailblazer people pioneering, you know, understanding wildfire risk to their operations, going back to, and I look at the case of SDG&E, who, you know, emphasized in a recent presentation that in 2003 was a turning point for them. They started to invest in, you know, FTS, remote automated weather stations, and of course they've expanded exponentially in terms of their weather network, using cameras and a lot of other situational awareness technologies. So really, you know, for me, I was looking at 2003 recently and going back in time. So I'd like to go back in a little bit of a time capsule with you all to look at how 2003 fire season impacted British Columbia, and how very quickly the situation can change week to week, and how lightning ties into that. So here we have a screenshot of our wildfire danger risk for the province of British Columbia at the end of June, 17 years ago. I'll fast forward another week. You know, they're still green and through very low risk. So you fast forward about a week of warmer, drier weather, and you start to see the fire risk build. The probability of ignition start to expand exponentially, going as we approach around this time of the year, end of July in this part of the world. And you'll see in the next slide that by the end of the month, in a very short period of time, we went from a very low wildfire risk to a very extreme. In fact, I remember as a provincial fire control officer being in the emergency ops center, and provincially our leadership group was looking at this new color, a dark brown red color that formed, and that was an interesting day for us, because we invented a new color thanks to the weather change. So we were sitting on unbelievable amount of risk. We have, of course, imported resources from across Canada and the US to help pre-position crews and resources to attack what was going to be not a very fun summer for us. In a very short period of time after that, we tracked lightning coming in from Washington State and Idaho, and it tracked right into our province over the border. Seem to be having a challenge to advance. Next slide. Oh, here it comes. So in that short period of time, in 2 weeks, we received 40,000 lightning strikes. With the resolution, might be very difficult to see, but you have O's and pluses. And for us in Wildfire, we were very much interested in the positive strikes, which means there's disturbance with the ground, which means we have a source of ignition. And with the conditions you could see there overlaying those lightning, the lightning map, we knew we were in a boatload of trouble there. So we responded as best we could with the resources we had, and we were constantly reprioritizing the resources. And this is where, and I won't go into it into detail now, but monitoring the weather and identifying where your risk is the highest and pre-positioning limited resources when you have multiple start days is really a good practice of prudence. So in that period of time, mid-July to close to mid-September, we had 17 wildfires. And out of the 2,500 fires we had, 44 of those were problem fires. And when I say problem fires, I mean large fires or fires that were in the wildland urban interface or both. We definitely had some overlap of both of those, with about 2,200 fires that were what we would call small, under 10 acres, 110 in the sort of 270 range, 36 fires over 2,000 acres in size, and 8 of those were over 24,000 acres in size. So, that was obviously a very difficult wildfire season for us. And I should mention that, in recent years, 2017, 2018 back-to-back seasons broke all the records from this season. So to put it in perspective, before I hand it over to our colleagues here, our daily maximums, this is just one day. We had 763 fires in 6 days. So you can do the math there, but our peak with new fires in one day was 218. We had 220 helicopters supporting the operations, 40 fixed wing air tankers, over 7,000 firefighters from all parts of Canada and the US, even Australia, and I believe we brought in the Mexican firefighters that year as well. That was the first year we did that. And 746 fires burning in that one day, with over 30,000 acres burned, and we spent about 10 million on suppression costs. So, that kind of encapsulates how bad it can get, and we know it can get worse, unfortunately. And to not leave out the United States, a situation which is also very grave, especially in Western USA, and we're tracking this. And I just thought this slide was very relevant to today's discussion, and certainly more contemporary look at the situation where, have all the purple dots there are wildfires over 100 acres in the United States. So this is, less than 100 acres. So that's, very significant. I think the symbol's incorrect there, but those are fires over 100 acres in the United States. So a very compelling slide there, I thought. So without further ado, though, I would like to now pass it over to Dr. Jeff Lapierre, lightning scientist with Earth Networks. Take it away, Jeff.
All right, thank you, Sean. So thanks, I'm happy to join you guys today. I will be talking a little bit about how lightning occurs, the different types of lightning, and how that relates to forest fires that Sean was talking about. So let's start at the beginning. So how does lightning happen? So you have our sun, beats down on the earth, heats up that earth, and makes an updraft. And so you have this updraft, and if there is enough moisture in the air, then that updraft brings that moisture up into the atmosphere, and it can condense into a cloud. And so you have your cloud starting up. Now, if that updraft is strong enough, and can get you above the freezing level, then you can start getting these little ice crystals. And so the updraft is the storm's engine that's providing this energy into the cloud itself. And then these ice crystals you can think of as the fuel for the electrification of this thundercloud. And so that's a big requirement. So once you hit this freezing level, you get these ice crystals. They can start interacting with the other micro particles in the cloud, like graupel and hail and super cooled liquid water droplets. And you can start getting charging. And that's where you get a thunderstorm. And so this is obviously very, very simplified, but this is a typical thunderstorm that you get, the charge structure of a thunderstorm. So typically you have around that freezing level, just a little bit higher than that freezing level, you get these negative charges with the top level of the cloud having positive charges and then a small layer of positive charge below that. And so that's your typical we call it a tripolar charge structure. Obviously, you can get much more complicated charge structures. We have 5, 6, 10 layers of charges. But this is a nice way to just go and look at things. So that's how a thunderstorm comes about. So let's talk about the different types of lightning. So the first type that is most relevant to forest fires is cloud to grounds. And so typical cloud to ground looks something like this. So you have the flash that for a negative cloud to ground, I'll talk about polarities in a little bit, but for a negative cloud to ground, you have the flash starts in between, generally between the mid-level negative and the lower positive down in the middle there. And so you have one branch of the leader of the lightning channel that goes up into the negative charge. And if the conditions are right, you have the lower channel that can come down to ground. And so as that channel is kind of creeping down to the ground, it starts inducing these upward leaders. And you can see that there's some upward leaders on the trees that are shown in the animation that didn't get connected. And so it's kind of a game of chance as to where the lightning will actually connect. Typically, it's the highest objects have the higher probability of getting struck, but that's not always generally the case. It depends on a lot of different things like the geometry of all the things around, where the channel is, things like that. But in this case, you know, the lightning, we have it connecting to the striking the power lines, and that's when you get your return stroke. So when it connects to ground, then you have a nice conductive channel from the ground to the cloud, and that redistributes the charge, and you get that big flash and that big sound that is easily associated with lightning, and that's called a return stroke. Cloud to grounds account for about 10% of all lightning, and I'll talk about its counterpart, that's the much more common one called interclouds in a little bit. The typical size of a lightning channel, so the cloud heights are usually around 4 or 5 miles. So that's about the height, the length of the channel, and then it can get about that size or even longer. Some of you might have seen the WMO world record for longest flash that I believe was 700 kilometers long. So they can obviously get much longer than this, but this is for a typical thundercloud. They're about 4 miles horizontal length also. And so if you think about the thunder that creates, the speed of sound is about 1 mile per 5 seconds or 1 kilometer per 3 seconds if you use that metric. So using this approximation of 4 miles, the thunder itself will generally last around 20 seconds per flash. And that's just simply because it takes the sound that long to travel the distance of the flash itself. And so one way to kind of estimate how big a flash is actually is by how long the thunder rumbles for. So if you have a lightning flash that rumbles on for like a minute, you can tell that it's a really long, really large flash. So I talked a little bit about cloud to ground polarities. So the picture I was showing earlier are typical negative cloud to grounds. We also have positive cloud to grounds. And so they're determined by which polarity of the leader goes to ground. So if it's a negative cloud to ground, that means the negative side of the leader goes to ground. If it's a positive cloud to ground, that means that's the positive side of the lightning flash that goes to ground. So this gives you kind of an example of a positive cloud to ground. So you can see that this time the flash is between the upper level positive and the mid-level negative. But in this case, you know, that negative side, the positive side of the leader made its way to ground and struck these trees. Now, why this is relevant to forest fires is because positive cloud to grounds are much more have a much higher risk of inducing wildfires. So while, as I'm showing here, they're only about 1 to 10% of all cloud to ground flashes, they are at a higher, they pose a higher risk for these wildfires and also for power line damage. Yeah, so they're cause a lot of problems with fire, structural damage, power line damage, things like that. They're much more dangerous. And the reason for that has to do with this phenomenon called continuing current. So when you have this return stroke, when you connect to ground and you have this large surge of current, that large flash, that large thunder, that current that produces all that only lasts on the order of a few milliseconds, very short amount of time. And while that return stroke current is really high, it's tens of thousands of amps. It's really high current. It's a very short amount of time. What makes continuing current dangerous is that you have this, it's a smaller amplitude. It's only about 100 to 1,000 amps only, which is still a large amount of current, but it lasts for hundreds of milliseconds. It can last for hundreds of milliseconds. And that's what makes it so much more dangerous, because for a fraction of a millisecond, you can have a lot of current, but it might not be enough to actually ignite, let's say, a tree. But if you have 100 amps or 1,000 amps for 100 milliseconds, that gives you a higher chance of actually igniting that tree or damaging that power line. So they're much more dangerous. So the reason why the positive cloud to grounds are more dangerous because of continued current is, while negative cloud to grounds are more prevalent, positive cloud to grounds more commonly have continuing current. Negative cloud to grounds don't have continuing current as often. And so even though they're more rare, they're more dangerous. And so that's something to keep in mind when you're looking at lightning data. If you see a positive cloud to ground in your lightning data, that kind of raises an extra level of a red flag for forest fire danger. So especially when these positive cloud to grounds occur in these high base thunderstorms that are called dry thunderstorms, where they basically, the rain, even if they do rain, it's so dry that the rain dries out and evaporates before it hits the ground. And so that's even more dangerous, because now you have these conditions where you can have lightning that's hitting the wildfires, but without getting that precipitation to kind of put out the fire or moisten what's being struck. And so those are even more dangerous. Those conditions, a dry thunderstorm or dry lightning conditions, are even more dangerous. So to give you an idea of what a continuing current looks like, we have a short video going on here. We'll start it up. So you'll see on the right side, yeah, so you see that flash, that really quick flash, and the slow current afterwards. So it really gives you an idea of the time difference, the difference in duration. And I'll play it one more time. Let's see. Here we go. So you see the flash on the right, that happens super fast. Maybe. There we go. So the flash will happen super fast, and then you have that low kind of dim current that lasts afterwards. And while it may not look that impressive, that can transfer a lot more charge to ground and be a lot more dangerous. All right. So another category of cloud to grounds is something called a bolt from the blue. And you can kind of see an image of this on the right. And so what a bolt from the blue is basically, it's termed that way because if, let's say, you got struck by that lightning, you would be in blue sky, because that lightning actually comes out the side of the cloud and travels anywhere up to as much as 15, 20 miles away from the charge center, from the thunderstorm itself. So it can actually strike very far away from the thundercloud itself. And so you would be in, clear blue sky. You'd be looking at the thundercloud from far away, but you could still have this danger of being struck. And those generally represent again, around 1 to 10% of cloud to ground flashes total. So they're not common, but they're also not uncommon. And so this is a really photogenic photo of some lightning going out the side of the cloud and striking down to ground. So that's why it's, even if the thundercloud isn't close to you, you have to be careful about these types of lightning. Okay, and so the final type that we will talk about today is basically the rest of the lightning, which is called intracloud lightning. And basically that is lightning that remains within the cloud and does not go to ground. So typical intracloud flash generally occurs between the mid-level negative charge and the upper level positive. So you can see the flash starts in the middle of those two and then extends upward and downward into those charge regions. That accounts for by far the most amount of lightning that we see, about 90% of lightning. And while intraclouds, again, it's not a direct threat to wildfires because it's obviously not connecting to ground. And it still makes thunder. There's still high currents. They're not as high as cloud to grounds, but they still produce thunder. They're a little bit quieter though. Now, like I was saying, they might not pose a direct threat to wildfires or damage to power lines. They're important for alerting. And so important for these DTAs, these dangerous thunderstorm alerts that I'll talk about in a second. So Earth Networks also produces this product called Dangerous Thunderstorm Alerts. So basically what they are data whenever the lightning is very active. We can track that lightning and produce alerts on that. So severe convective storms like hail, high winds, tornadoes, they're often associated with lightning and lots of lightning. And so, and while measuring the cloud to grounds is important for determining where the wildfires might happen, the intracloud lightning is really what tells you when this strong convection is really happening. So if you're only using cloud to ground lightning, you might not be able to tell when this is happening. It's really important to have total lightning, the combination of intracloud and cloud to ground. And so you can use this information to really tell you and warn you when severe convective threats are really available. And that's really what these dangerous thunderstorm alerts are all about. And I'll go into a little more detail here. So how this works is there is an algorithm that's just always looking at the lightning data, and it's measuring the flash density. And so if you get a high enough flash density, like is shown on the left here, the algorithm will deem this as a lightning cell. And so once that lightning cell is created, it can start tracking things like the number of cloud to grounds, the number of intraclouds, the flash rates that are occurring within that cell, and things like that. And it can also look at just purely from the lightning data. It can look at the speed of the cell, the velocity of how fast it's traveling, the direction of the cell. So it keeps track of all this stuff. And if that flash rate reaches a high enough level, it will start creating these lightning cell polygons that you see on the right. And so these polygons are shaped, as these kind of long, elongated squares, and their shape is determined by the size of the cell. So the width of this polygon depends on the size, but then the length itself depends on the velocity of the cell. So this cell always alerts out to 45 minutes. And so the length of that cell depends on how fast it's moving. So if it's a fast moving cell, it will be the 45 minutes will track out farther than if it's a slow moving cell. So that gives you an idea of how quickly the storm is moving towards you. And so as the flash rate continues to increase and increase, these polygons increase in level and basically are telling you these cells are becoming more and more dangerous, to the point where if the flash rate is above 25 flashes per minute for certain conditions, or as much as 45 flashes per minute in the summer in the East Coast, then you have a DTA, and that's very high chance of convective and dangerous conditions, convective conditions. So we did a study using our DTAs and compared against the National Weather Service. They produce their own alerts. They use a lot more data. Where we use only lightning data, they're using radar data, modeling data, and they have people that are issuing these alerts. So they're always having, their forecasters are looking at not only, they actually use lightning data also, but they're looking at lightning data, they're looking at radar data, all these things. So we wanted to compare our automated only lightning alerts to the best of the best, which is the National Weather Service. And so what we found is if we split them up into different categories of severe weather, so we have tornadoes, hail, and then severe wind, we can look at the alerts that both networks, Earth Networks DTAs and the National Weather Service alerts, they both detected, and look at the lead time. What was the earliest alert that detected that actual ground truth verified severe weather? And so what we found is, on average, Earth Networks is detecting several minutes earlier. So for tornadoes, we're alerting 8 minutes before the National Weather Service, or earlier than the National Weather Service. For hail, it's 7 minutes. For wind, it's 5 minutes. And then you can also look at different zones. So this graph on the right just gives you different zones throughout the US. But the basic takeaway here is blue is for the DTAs, and so higher is better. And so the blue bar is always higher. So we're generally in all regions of the US detecting earlier. And that has to do with things being automated versus a person doing it. And maybe the person has some reservations as to setting out an alert, whereas the automated one just sends it out. So getting things early is important. That few minutes is very important. So now getting into how climate change may affect the forest fire frequency and magnitudes. So the obvious trend, or the obvious correlation here would be, as the temperatures rise, you get warmer temperatures, the surface dries, and then things are easier to initiate. But it's not only that, there are actually it's more complicated than that. There are things like the warming season and the hot season for when forest fires can occur, it actually gets longer. So you have a longer wildfire season. Also, there are studies that are predicting that if you assume, twice as much CO2 in the atmosphere by the end of the century, there are research studies that we have linked below that predict an increase in lightning frequency by about 44%. So that in turn would lead to an increase in area burned by about 78%. So we're really seeing a strong effect by this increase in lightning. So basically what's happening is not only is the regions that are being warmed just getting drier, but you also have, remember, the sun is what's driving this. The updraft is really what's driving this. So you have a greater potential. You have a lot more, this engine is a lot more strong for producing these thunderstorms. And a similar study showed that about 72% increase in cloud-to-ground lightning over the continental US for these same conditions prior. And an important thing to keep in mind is the majority of forest fires, especially in regions in like Canada where there's a lot of uninhabited forests, that they are by far the majority, the high cause of what these forest fires are. So this slide has a lot of information. Mostly, I want you to keep focus on these red bolded information, these statistics. These come from, again, a peer-reviewed publication. So basically, this study looked at in 2 different regions, Alaska and Canada, and looked at what variables or metrics correlated positively or negatively with fire counts. And so if you look at that very first column, you can see that for total lightning strikes, the very top, there's a really high correlation of 0.93. The highest correlation you can get is a 1. So 0.93 correlation with fire counts, as well as regional fire radiative probability flux, is that what that second column is. They're basically, they're metrics for measuring wildfires. They correlate really strongly with total lightning, and even more, or almost as strongly as CAPE, which is basically a measure for this convective potential. So basically a measure for this engine, how strong this engine is. So the last thing I want to touch on are these things called pyrocumulus clouds. And so what basically that is a thundercloud that was created by the thunderstorm itself. So basically what you have here is you have your fire. That itself is a source of convection, right? Because it's hot, so it's making all this air rise. And so you have this smoke plume that's rising. As it rises, it gets higher to the atmosphere, so it cools, it expands. Remember, if it gets above the freezing level, then these ice crystals can form. And so basically you have the same conditions that you have for thunderstorms. And so you can have a thunderstorm that's created by the wildfire itself. And so how this is relevant and especially dangerous is you can have two things. So you have these downbursts where you have sudden bursts of precipitation that come down, and that the winds from those downbursts can actually spread the fire. So the thunderstorm itself can actually influence the spread of the fire itself. And then finally, you can have lightning, obviously, that can be created by these pyrocumulus clouds, and far away from the original fire itself, and that can as well start up its own fire, and again continue to increase these fires themselves. So this is a real thing that happens, and something that forest fire management teams really have to worry about. So that is the end of the information that I wanted to present to you. So thank you very much for listening, and I'm now going to pass it off to my colleague, Steve Principali. Steve, take it over.
Thank you, Jeff. Once again, Dr. Jeff LaPierre, great colleague, friend, lightning scientist at Earth Networks, and really a wealth of wonderful information, Jeff, that you provided there. I think we all have a new cloud that we learned today, pyrocumulus, so really fascinating. And this is important for us as we, again, move through fire season, to be aware of the risks, to be aware of the terminology, and obviously for mitigation, which is what Sean talked all about. And we're a team here. We work together to try to empower you with the tools to keep you, your loved ones, your assets, as well as your customers safe. So that leads us into this first question here. Are you currently using commercial weather data to help you identify severe risks like lightning? So this is a poll question we'd like you to take right now. Think about this. Is your organization currently utilizing commercial weather data alerting to help identify severe weather risks, such as lightning? Yes, no, or are you not sure? And this is a live poll, so we'll provide the results here for you shortly. But this is definitely going to give us some food for thought, so to speak, going forward. And if you don't, it's okay, because this is what we want to help you with. About 59% said yes, and 15% said no, and there's about a quarter of you that just aren't sure. Well, no worries. We're going to take you through again and give you an idea as to how you can be empowered to have your organization have the tools and the technology to be able to do such. So that's really what the focus of the last part of this webinar is going to be about. And I want to introduce you to some of the tools here shortly. But first, just showing you, Spheric Maps is our high-powered tool that is hyper-local, provides real-time tracking of the lightning, the weather data from our huge network of weather stations. It allows you to visualize where there are storms, such as dangerous thunderstorms that Jeff talked about. We have lightning maps between 1 and 60 minutes, radars available, as well as predictive maps for things like rain, freezing rain, snow. Very helpful all times of the year. Our alerting is really one of the most robust features. We offer real-time alerting for lightning, say within 10, 15, 25 miles. Remember, Jeff talked about those bolts from the blue. Friends, they can strike 15 miles from a parent thunderstorm. So it's very important that you are aware when there's lightning in cloud or cloud to ground within, say, a 15-mile radius of your locale. And therefore, you can get your family, your friends, your assets to a safe location to secure and minimize, obviously, potential risk. We also have alerts for 19 hyperlocal conditions, everything from wind chill and heat stress all the way down to precipitation rates. So that's really helpful as well. I mentioned the dangerous thunderstorm alerts that are automated alerts for 45 minutes, real-time alerting for NWS, National Weather Service variables, unlimited alerting to subscribers via text and email, just a lot of good information there. And additional functions such as hurricane tracking. We have our 7th tropical storm today, Gonzalo, that we'll share with you here shortly. Live camera views, historical data, and historical lightning data as well, and custom layers that you can upload. We'll show you how to do that here shortly. First, I mentioned the bolts from the blue, as Dr. Jeff LaPierre did, and I want to show you some range rings for maybe an example of how you can protect your company, your customers, utilizing Spheric maps and the Earth Network's Total Lightning Network. We have a range ring here, actually 3 of them. One is 10 miles, one is 15 miles, one is 25 miles. This is what you might set up. Within 25 miles, you might have an email sent to your network operations when there's lightning detected in cloud or cloud to ground within 25 miles. An email alert is sent out. That's just saying monitor the situation, be prepared to take shelter, be prepared to take protective action. Okay, so you're aware of that. Middle ring is the 15-mile ring, and that's when a text and an email alert gets sent out to key stakeholders so they're aware to monitor the direction, the track of the storm, its intensity, and prepare rather swiftly to move to secure areas. And then certainly, friends, if lightning's within 10 miles of your location, you're inside, you're away from windows. We have pushed those alerts out to your emergency, public safety, outage resolution teams. You guys are all aware of what to do, where to go. There will also be an all clear announced, obviously, when lightning has stopped. But the point is, you are aware to clear the area, get inside and away from windows, and at least you'll be able to have the peace of mind that you, your company, your assets, whatever you're concerned about, are going to be protected during this. And then you can do a post-event review utilizing Spheric maps and take a look at the lightning data. Where was there the lightning data? Were there the positive CGs that Jeff LaPierre talked about? Those were the ones that can produce often the continuing current. Did that trigger a forest fire? So you can go back and do a post-storm analysis and really glean and get good information on what happened over your area. And then finally, we also offer Ncast, and that is really pinpoint forecasting utilized by a lot of utility companies, electric companies. What it is, it's a forecast that goes out 2 weeks in advance, believe it or not, and it's broken down hour by hour, updated twice a day, gives pinpoint forecasts for your neighborhood. Real-time information from our weather observation network is collected. It's pumped into a sophisticated modeling algorithm, and then we provide forecasts, and the accuracy is quite good. It's improved over traditional models. It's a great feature that we have here at Earth Networks that I know a lot of our utility companies are indeed leveraging. So now, friends, I want to take you on a little bit of a tour utilizing Spheric maps so that you can see how this actually is such a powerful tool. I'm going to share my screen here, and I want you to take a look. This is Spheric maps. Again, it is an online tool, so you can utilize this on your phone, on your computer, and what you're seeing right now shows just a basic map, but let's add some layers to this. So this is for webinar purposes. I'm going to put on the temperature layer. I'm going to put on maybe the radar. You want to be able to track storms. Let's get down to the radar layer. There it is. We're going to pop that on there as well, as we have an active day in parts of the country with storms. Obviously, we care a lot about lightning, so let's get that on. Again, I'm scrolling down the left-hand side of your map layer. Let's put on lightning flashes and pulses, lightning cell tracks, and lightning alert polygons. We'll put them all on there. I'm also going to put on for severe weather. You scroll down here to the very bottom. Maybe you are concerned about current fires, so you can put that layer on as well. There are fire perimeters as well and complex points, so that's very helpful. I mentioned there's also an active storm in the Atlantic, and there it is. This is Tropical Storm Gonzalo that you're seeing right down here where I have my mouse. It is right now a tropical storm with winds of 50 miles an hour moving toward the Windward Islands. So we have the ability to track tropical storms as well. and also lightning reports. I'll show you how to run that here in just a second. First, I want to show you one of the great features of Spheric Maps. I saved a special view that has lightning and dangerous thunderstorm alerts. So this is called my webinar view for DTAs, or dangerous thunderstorm alerts. And look at this, voila, we've got some on here. First, I want to show you the temperatures. Right now it's 91 degrees in Frederick, Maryland. And I want to show you as well, if you click on the details section of this link and go to the online weather center, you can actually get a web camera from a nearby school. You can play this through. And again, we have a network not only of weather stations, but also of lightning, greenhouse gas, and camera stations that really help for situational awareness. You can also see the active alerts, a flash flood watch, a severe thunderstorm watch, a heat advisory. All that is available. But let's go back to Spheric Maps, and I want to really focus in on the dangerous thunderstorm alerts that you are able to see here. So I'm going to zoom in using this plus sign on the left-hand side. And here's one dangerous thunderstorm alert just moving toward the York metro area, right over Hanover, Pennsylvania. Take a look at this purple polygon, friends. This denotes the 45-minute automated alert that Dr. Jeff LaPierre talked about, the dangerous thunderstorm alert. And this is clickable, so that when I click on this, I get some information. It goes out through 2:25 this afternoon, Eastern time, starts at 1:40. So I want to get some more information. Click on the details, and you can see that this storm has an increased potential to produce severe weather, just as Jeff was talking about. Frequent lightning, heavy rainfall, damaging winds, all a threat right there. So you can get this kind of great information on our network, updated in real time. Also, if you see this lightning cell, another aspect of Jeff's presentation that he talked about, this really helps you identify the lightning flash rate. So you're able to see, for instance, things like where the lightning is located, what's the flash rate of this particular storm, get some details on the flashes. So this has been very helpful for us in terms of tracking storms and identifying dangerous storms. If this is something that you are concerned about, then I would encourage you to check out Spheric Maps. I'm just clicking, by the way, on this lightning polygon here. And what I want to show you is a history of the flash rate. Check this out. This shows you the power of Earth networks. We detect, as Jeff was saying, both in cloud and cloud to ground lightning. So if you look on this map, what it shows is really a time series going back to about 1:30 in the afternoon of lightning, featuring both cloud to ground. That's that lower one that's in the yellow that you see there. Very low flash rate, generally between about 3 to 7 flashes per minute. And the IC flash rate, which is just prolific, that you see in the red dash line there, that is between about 12 and maybe up to about 35, 37 flashes per minute. So that's triggered our DTA, the dangerous thunderstorm alert that we were mentioning, for a flash rate east of the Mississippi, or in eastern areas, of 40 flashes per minute. So I want to zoom back out and show you there are also plenty of other features here that you can add. I've got a lot of information on this map, so I'm just going to simplify it and take off the temperatures. We'll take off the cell tracks. We're going to take off the DTAs just for the time being, but I want to show you another feature that we have, which is called Storm ETA, estimated time of arrival, obviously. And when you zoom in on this feature, look what you can see. You can see things like when a storm is going to arrive in a certain area, in a certain community, by time. Each one of these little lines denotes when this algorithm believes a storm will arrive in your community. And I should mention, you're seeing the lightning data. I want to move this to the top as well. So I'm going to go over here, move the lightning data up to the top, and you see a lot of the purple, these double arrows. That's the IC, or the in-cloud lightning. And occasionally you see some yellows that denote CG, and right there, that's a positive CG. So that could contain, and here's another positive CG, some of that continuing current that Dr. LaPierre was talking about. So I've showed you lightning, storm ETA, dangerous thunderstorm alerts. I want to show you how to add a custom layer. Up here, you can add a GeoJSON file, and I've actually already done this for utility lines out in California. So I want to take you to this. It's as simple as just loading a file onto your laptop, and look at this. You can have your assets plotted there so you can see California transmission lines. So easy, so useful for identifying fires. And speaking of which, let's pull a lightning alert, a historical lightning alert. So let's go over here on the left-hand side of Spheric Maps. Again, this high-powered hyperlocal tool. I'm going to go to Lightning Archive, click on Report, click OK, and it's as simple as this. When the report comes up here, I'm going to pull a lightning report for my specific area. Let me just click on it here, and I'm going to go over here and get a box. And with this box, I'm going to actually draw a lightning area that I would like to pull historical data. So let's just say here in Northern California, I want to pull this area for historical lightning data, and you're able to do such, fill out the information, and then you will get an email sent to you. And then when you load the email, you're able to retrieve the weather and the lightning data, again, with the same symbology, whereby the purple or magenta denote in the cloud, and the yellow denote cloud to ground strikes. And you can load it into Google Earth or have a CSV file, whatever is your preference. But the point is, you can go back and you can compare and look at, see how the lightning compared with where transmission lines were. So you can see the value of this utilizing Spheric Maps. So again, very high power tool. I tried to give you a quick overview there because there's so many great features to show there. But again, the ability to add a custom GeoJSON file, the ability to pull a lightning report from a certain time is really going to be very valuable. And it's something that I know you will appreciate and be able to utilize. And it's something that is also very useful to any organization that is interested in having such lightning information there. So I'm going to go back to the actual PowerPoint presentation. And I will show you in the PowerPoint presentation.
Hey, Steve, it's Anna. Hey, we're running a little short on time, so I think what we should do actually is jump right into questions, if that's okay. Sure. We do have questions, and I do want to make sure we get to those questions. So let's just move right on to questions. And so we have a few questions already. If you have a question you'd like to ask, go ahead and put it in there. The first question is, are there certain conditions that can influence whether a cloud to ground strike will be positive or negative? And I guess that one was for Dr. LaPierre.
Yes, thank you for the question. That's a really good question. So there are places that have positive cloud to grounds that are more prevalent. One that comes to mind really quickly is the Colorado area. That has to do with how the storms they charge in we call it anomalously charged thunderstorm. So where you have this tripole structure where you have negative in the middle and positive on both sides. It charges the opposite way where you have positive in the middle and negative on both sides. And there's still some research going on as to why that region has those kinds of storms. But the prevailing thoughts has to do with the microphysics, how the Colorado region is very dry, so the cloud bases are very high, things like that. But the Colorado region, yes, does generally have much higher prevalence of positive cloud to grounds.
Okay, thanks for that. And I did want to also mention, as more questions come in, that we did put our handout here, which is our 2019 Earth Networks U.S. Lightning Report, and that has all the lightning that we detected in the U.S. There's also a county level map for each state. So if you're interested, you can chat to me here and we'll get that to you. But the handout is there. You can read what our network did detect. The next question looks like maybe again for Dr. LaPierre. Is there a weather model that can more accurately predict lightning occurrence in the USA or Canada?
A weather model that more accurately predicts lightning. Actually,
Steve.
I'll push this off to Steve because of his meteorological background.
Hi, Jeff and Anna. Yeah, that's a great question. I would say this: any model that utilizes excellent boundary layer parameterization, the NAM would be an example of this. That's a North American mesoscale model. Any high resolution model, that is to say, when you think about a model almost like a checkerboard and having a lot of points of data and points of information, the more data that's fed into a computer model, the better it's going to be in terms of being able to identify where there could be lightning or convection or storm. So I know myself in the summertime, I do like to rely upon those models like the NAM, the North American Mesoscale model, or a model that has very small resolution or fine resolution. So that can help to identify where there could be storms that could trigger lightning. That's probably the best way to answer that question.
Okay, thanks so much, Steve. The next question is, what is the accuracy and distance for pinpointing lightning downstrike locations?
I'll take that one. So for our network, we can measure things down to the hundreds of meter level. So because of the way we detect lightning using time of arrival and the frequencies we use, yeah, we can get down to hundreds of meters location accuracy. So a couple 100-meter location accuracy.
Great, thanks. The next question is, are you seeing a greater amount of strikes when dealing with new mega fires?
With mega fires, I'm not familiar with that, but so my initial thinking on that would be that these mega fires are very large, and so the heating, when you're talking about these pyrocumulus clouds, the idea is you have this kind of point source, not point source, but for a lot of these fires, you have very small localized convection, and that's what causes this instability, because it's, you know, it's heating the air in a local area and producing this thunderstorm. Whereas you have these huge fires, they're producing heat all over the place, and so it's kind of more, it's a lot of heat, but it's a lot more uniform heat distribution, and so that kind of dampens the ability for these really big storms to produce pyrocumulus clouds.
Yeah, and if I could just jump in there too on that one, Jeff and Steve, if you don't mind, like from an operational point of view, absolutely, with pyrocumulus clouds, you're having an increased chance or risk of lightning strikes, starting secondary or tertiary fires outside the main fire perimeter. It's also a major cause of concern when you're using extensive aviation resources. They're battling the fire. That's a safety issue that's always highlighted from an air attack point of view, identifying risks out there. Another thing I'll add to that too is that with the pyrocumulus forming, just by the nature of that happening, all that convective heat rising up into the atmosphere, you're getting a big change in wind, as you guys all know. It's not just the prevailing winds and all the other winds that are in your upper level and lower atmosphere. You're getting wind generated on site, and that's exactly why big incidents complexes and incident management teams will have a fire behavior analyst on site, which is essentially serving as kind of the local Met service, but also predicting wildfire behavior as it relates to wind and the fuel and vegetation around in that topography. So very important.
Thanks a lot, Sean, for that. The next question is, do you use deep learning or ML models?
So we haven't started using that, and we don't use that in any of our current products, but we, as myself, I'm part of the research and development group at Earth Networks. We have started looking into using deep learning for certain regions, certain products that we're using, specifically for maybe the next generation of our dangerous thunderstorm alerts, possibly the next generation of our lightning classification, how we determine when a flash is an IC or CG, things like that. So that's definitely something that is being looked at the company.
All right, the next question is, can you talk about your major and minor ellipses for determining lightning strike accuracy?
Sure. So the major minor axes that come with all of our lightning pulses, our pulse data, that gives you an idea of the error ellipse that encapsulates where we think that location is at a 50% confidence interval. So with a 50% confidence interval within that error ellipse, whatever orientation is or anything like that, that gives you an idea of, you know, there's a little bit of error in the location, and so we provide these error ellipses to give you some kind of confidence as to where we think that location is. And so that's what those aerial ellipse data represent.
Okay, thank you. I do know we're running up against the end of the hour here. I do want to thank our presenters today, Sean Bethel, Dr. Jeff LaPierre, and Steve Principali. I do also want to mention, I know there are some upcoming webinars. Sean, did you want to just invite those for the next one?
Yeah, absolutely. As I mentioned, this was number 3 of about 12. Another one coming up, dates to be confirmed, but understanding wildfire weather and fire behavior. We're going to do another situational awareness piece with more of a focus on camera systems, cause and effect from wildfires. We'll be looking at post-fire and flood monitoring, forecast and alerting tools. That'll probably be more like end of August. We're going to do one on air quality associated with wildfire events, and another one on enhanced emergency management, making critical decisions at critical times. The one key one I wanted to highlight, and more for the utility audience out there, is we're going to do a very utility wildfire mitigation planning piece. It's a 2-part series. It's called Wildfire Mitigation, Wildfire Risk, Safety Culture, and Innovations for Utility Operations. So that'll kick off September 10th as part 1, and September 17th will be part 2. Part 1 will be weather monitoring and vegetation management, understanding wildfire risk to utilities in our communities. And on September 17th, part 2 will be fostering a culture of safety and utility operations, bite-sized technology innovations that support wildfire mitigation efforts.
That's great. Thanks, Sean, and thanks everybody for attending. We really appreciate it. We will send out the recording. We will send out the slide deck if you have any feedback. We love feedback. info@earthnetworks.com, and we hope that you'll come back and join us for another one. Thank you so much, and have a great afternoon.
Thank you.
Thanks, everyone.
Have a good day.